Hello, this is Chen from Snowflake. Today I will talk about our work breaking down memory walls, adaptive memory management in LSM-based storage systems. The log structure memory tree is a router optimized structure based on out-of-place updates. It has a memory component that stores incoming writes. Whenever it is full, it can be flushed to disk to form some disk component. A disk basically contains multiple levels, each of which contains a couple of partitioned SS tables. So whenever the disk level becomes full, one SS table can be merged into the next level. Efficient memory management is always critical for storage systems to achieve good performance, but different from traditional storage systems with in-place updates, LSM-trees have introduced some additional memory walls. In this work, we want to break down these memory walls to get better performance. This is a typical architecture used by today's LSM storage engines. The global memory will be divided into a random memory region to store the memory components and a disk buffer cache region to cache the immutable pages from the disk components. But this architecture contains several memory walls. The first memory wall is the static size allocation for each memory component, which is commonly used by today's LSM-based storage systems. The second memory wall is there is no efficient sharing of the random memory of multiple LSM-trees. The last memory wall is between the random memory and the buffer cache because typically these two regions are statically allocated. In order to break down the memory walls, we introduce adaptive memory management architecture, which contains a couple of differences with the previous one. First, we do not set any static size limit for each memory component, but instead we let all the random memory share the same global random memory region and adaptively flush some memory components when based on the workload. So this will allow efficient sharing of the random memory based on the workloads. We further introduce a memory tuner to dynamically tune the memory allocation between the random memory and the disk buffer cache. So this is break down the third wall between these two regions. Let's look at the first problem. How do we manage the random memory efficiently? Random memory directly impacts the write-out cost. That's why it is important to utilize the random memory efficiently. First, how do we maximize the memory utilization for a single LSM-tree? Existing LSM-tree implementations typically use B-trees or skip lists to store the incoming writes, but this design reduces the memory utilization because of two problems: internal map fragmentation, and they will free a large chunk of random memory at once. Second, how do we allocate the random memory to multiple LSM-trees to minimize the overall I/O cost? These LSM-trees may have different sizes and write rates. And existing LSM-tree implementations typically use a max memory flush policy that always flush the LSM-tree with the largest memory component. But we found this flush policy is not ideal. In order to solve the first problem of maximizing the random memory utilization of a single LSM-tree, we propose to use an in-memory partition LSM-tree to manage the incoming writes. Its idea is very simple. We introduced a partition LSM-tree as part of the memory component. The key intuition is that the LSM-trees generally achieve much higher space utilization than B-trees, and we want to trade some CPU cycles to minimize the merge I/O cost. As you can see here, this structure, its memory component contains a multi-level partition LSM-tree. It has an in-memory active asset table to store the incoming writes. We can do the memory merges as we did for the disk merges. And also, whenever the random memory becomes full, we can select one asset table to flush it to disk. This design allows us to do the partial flushes, which means we can flush one asset table at a time so that the RAM memory can stay full. Now let's consider some alternative flush policies to manage the RAM memory of multiple LSM-trees. The first intuitive flush policy is basically the main LSM. We always flush the LSM-tree with the oldest LSM. However, it is not clear whether this main LSM flush policy is already optimal or not. So in order to solve this problem, we formulated this problem of memory allocation as an optimization problem to minimize the overall route cost. So I don't want to delve into the exact math here, but there is some interesting conclusion. Assuming all the LSM-trees, they use the same merge policy, which is pretty common, then the random memory allocated to each LSM-tree should be proportional to its write rate. which means a hot LSM tree should get much more random memory than a cold LSM tree. Let's look at some experimental evaluation. The first, the baselines. So the first baseline is the BJ static, which is the static memory allocation scheme used in AsterixDB by statically allocating the random memory to a configured number of active data sets. We also have the default and the tuned. The second one is BJ dynamic, which is an optimized version of the existing scheme by basically not limiting the size of each memory component, let it grow dynamically based on the workload, but internally it uses the B tree. We also have the partition memory component structure. For BJ dynamic and partition, we also have evaluated the different flush policies. Let's first look at the experiments using a single LSM-tree. And as you can see, the partition memory component structure always improves the write overall throughput for the write-heavy workloads, basically write-only and write-heavy, by better utilizing the write memory more efficiently comparing with other baselines such as BJ dynamic and especially the BJ static. For multiple LSM-tree keys, we use 10 LSM-trees with different hotness and real memory sizes. And again, based on these two graphs, we can see a couple of things. First, again, the partition memory component structure itself improves the write throughput. And also the two proposed flash policies, they also improve the throughput by better allocating memory among LSM-trees. Especially the improvement becomes more obvious if the random memory becomes larger or the workload is more skewed towards a small number of LSM-trees. Finally, let's look at the memory tuner to break down the memory wall between the random memory and the buffer cache. Given a total memory budget, our tuning goal is to find some optimal memory random memory size to minimize the weighted hour cost per operation. There are also some ways to allow the tuning goal to be configured for different use cases. Since the workload, the optimal memory allocation is heavily workload dependent, and we basically use an online tuning approach to perform the continuous tuning. Its idea is that we can let the memory, the random memory on the buffer cache periodically report the workload statistics to a memory tuner so that the memory tuner can do the memory tuning like continuously. Here I want to give you some basic idea of how the memory tuning is done. Suppose this is the cost function with different random memory sizes. Intuitively, if you allocate a very small random memory, you will have a large I/O cost because you're going to do a lot of merges. And if you allocate a lot of random memory, it also has a large I/O cost because you're going to do a lot of cache misses or a lot of reads. So an optimal X has to balance the write cost and read cost. Now, I won't give you the exact details how the mathematics work, but I'm going to show you some basic idea. So if we can measure the cost derivative of the cost function, then we can basically do the continuous tuning of the memory allocation. So in order to convince you, I'm going to show you some results of the cost function in practice. We did a bunch of experiments using the YCSB, and as you can see, in general, both YCSB and TPC-C, they follow their cost function basically follow the same U-shape, which allows their tune memory, which allow their workloads to be effectively tuned using some continuous tuning method. We also did a bunch of evaluation of the memory tuner using the TPC-C in terms of its accuracy by comparing with some manually tuned baseline and some manually chosen baselines. As you can see, the memory tuner achieves near optimal I/O cost and throughput compared with the manually tuned baseline, and also it's much better than the two heuristic-based approaches. So to conclude this work, in this work we break down this we want to break down the memory walls of LSM-trees to enable adaptive memory management. The key contributions include adaptive memory management architecture, new memory component structure with new flash policies, and also with design a memory tuner to do the continuous memory tuning between the two memory regions. So if you are interested in this work, please check out the paper for more information about the techniques and also the evaluation. Thank you.